Greetings everybody. My name is Simon Selman from the Innovation Center of Faculty of Mechanical Engineering from the University of Belgrade, and I'm here to present to you two papers, the first of which is titled The Experimental Determining of Fracture Behavior of P460NL1 steel welded joint specimens. Now this was a part of my PhD thesis, one of the many experiments that were completed as a part of the research, and this one involves the impact energy tests on an instrumented Sharpie specimen. As you can see, the welded joints, the specimens were cut from a plate welded by using P460NL1 steel, which is typically used for pressure vessels working at lower temperature. It's a fine-grained microalloy steel with increased plasticity, and VAX 65 was used as the filler material due to its similar but slightly better mechanical properties and very similar chemical compositions. Now, the welding procedure used in this case was very similar to the one presented by the first presenter here, so metal arc gas welding with the M21 gas mixture. This procedure was selected because it is suitable for microalloy fine-grained steels and because it's very efficient and, of course, cheaper than the alternatives. Now, when it comes to the specimens that were themselves, there were several factors to be taken into account when the notches were placed in these specimens, and for that reason they were divided into 4 different groups. Now, the 2 main criteria were the temperatures that were measured during the welding process on one end of the plate and on the other end of the plate to see how this would affect the behavior, because the higher temperatures at the part near the end of the welded joint resulted in a slightly different welded joint geometry. For example, the heat affected zone was almost 50% wider in that case. And of course, the position of the notch in the heat affected zone was also important, as there were 2 possibilities, either in the root side or the weld face side. So for this specific experiment, which was conducted at the Military Technical Institute in Belgrade, the total impact energy was measured along with its components, the crack initiation energy and the crack propagation energy, and the idea was to see how the relation between these 2 components would change depending on which of the 4 groups of the specimen were in question. So for all specimens but one, it was confirmed that the joint was of very good toughness as expected, with values ranging from around 165 to 200 joules, although this doesn't include only the heat affected zone but also the weld metal and the parent material. For the heat affected zone, it was between 170 and 190, which we will see a bit later. So, of course, as expected, the dominant component was the crack propagation energy, which was typically several times higher than the crack initiation energy, although there were some differences between them depending mainly on the position of the notch, whereas the temperature effect didn't have so much effect in this case, but we'll see that later. So here you can see the welded plate, and these 8 points that are labeled here represent the points where the temperature was measured. You can also see the dimensions of the standard Sharpie specimen, the small one, 10 by 10, although it should mention here that our notch was not 1.5 but 1.4 millimeters, so that it would fit within the heat affected zone. And of course, this was all done in accordance with the standard, the ASTM E182013. So here you can also see the chemical composition and the mechanical properties of the materials which were used. So the parent material, as I said, low carbon microalloy fine-grained steel, and the appropriate filler material, the VAX 65 electrode. And here you can see that they do indeed have very similar mechanical properties as well. So the welding procedure itself involved a root pass and 5 additional filling passes. And during this process, the temperature was measured using a contact thermometer to see if there would be any differences on the opposite ends of the plate. And as I said, there was a total of 12 specimens divided into 4 groups. So with the notch in the weld face from location 1-1, which was the location of the lower temperatures. Then the second group was the same, but the notch was on the root side. and groups 3 and 4, with specimens 15 through 17 and 18 through 20, were taken from the part with the higher temperature. Group 3 had the notch in the root side, and group 4, again, in the weld face side. Now you can here you can also see the results of the temperature measuring at both locations from the opposite end of the plate, and you can see that there is an obvious difference in the temperature, even though the heat input was, of course, the same and the constant during the whole process. You can also see the cooling times, but I will leave that for some other occasion, because the effects of temperature are just a single part of the whole story, and we're still working to figure out how exactly they affected the whole welding process, in this case, of course. So the impact tests were performed at the instrumented Sharpie pendulum with all of those 12 specimens, and a couple more from the other regions, but I won't go into that much detail. And once again, the main focus was on the crack initiation energy and the crack propagation energy, and of course the total impact energy as their sum. Here you can see an example of the results from one of the specimens from the first group, which in this case was specimen 7. You can see the diagram showing the dependence of and the increase of impact energy with time. There is also a lot of other diagrams, like the force displacement or deflection in this case, force over time, but really don't have time to go through all that. So here you can see from one of the specimens in the second group, you see that they actually look very similar to one another. Here, of course, this is from the third group, that's specimen 17, and this is specimen 19 from the fourth group, which again is similar, although the values are a little bit lower in this particular case. So here you can see the overview of all of these 12 specimens with their impact toughness, the total energy, and the components. Now the specimen marked heat affected zone 20 has shown a bit of a different behavior. You can see that the values are much lower, although the ratio between the components is pretty much the same as in case of other groups. Now this is probably caused by some sort of a defect, because another specimen that was labeled as 21, which was used for fatigue test, also had shown different behavior. When during fatigue, the crack just at one point simply stopped propagating, and when we broke it later for photography, it broke in a very strange way. It's just like split, horizontally, if I can explain that, similar to what happens when you have manganese sulfide inclusions in metals similar to this one, although I'm still not sure that was the problem in this case. But those two specimens were very close to one another in terms of location, and they both gave us much different results, so maybe that's an interesting topic on its own. You can see that the rest of the results are far more homogeneous, and that if we take the average values for each of the groups, they would range between 171 and 182, if I remember correctly. And also you can see that the crack propagation energy is typically much higher, but now we'll see how this was affected by each of the groups. So the maximum total impact energy was measured, both maximum and minimum came from the same group, the first group, and it was specimen 9 that had the highest and specimen 8 that had the lowest. And yet on average, these didn't differ too much from the rest. Of course, as I said, the specimen 20 had its own story, but still its ratio was very similar to the other groups. The crack propagation energy was almost 3 times as much as the crack initiation energy, which of course was the case also from the first group specimens. So when the notch was placed in the welded face, the crack propagation was considerably higher. You can also see here that the maximum force values for root specimens were higher than those for the weld face specimen. So groups 2 and 3 had higher forces, and their values were slightly more homogeneous on average. So groups 1 and 4 had more favorable crack propagation to crack initiation ratio. It was 2.5 to 3.25 times higher, which suggests good plasticity as expected and high resistance to crack propagation. For the root, for the specimens with the notch in the root side of the heat affected zone, this ratio was not so in favor of crack propagation. It was 1.2 to 1.85 times greater. However, the crack initiation energy itself was a bit higher. So in total, the impact energy was almost the same, maybe even a bit higher. Now, as far as the temperature goes, the specimens that were taken from the higher temperature region had slightly higher ratios. For example, the 3.25 you see here, that was for group 3 specimens. So as far as temperature goes, it had a small positive effect on the plasticity and ductility, although that wasn't really so much noticeable. The position of the notch in regards of whether it's on the root or the face side had a bigger influence. So, as we can see from this research, which of course is a part of a much bigger research involved with my thesis, some of you who were at the ECF 22 summer school could have actually witnessed the fatigue test at one point. So it involved the making of 12 specimens, which were divided into 4 groups with notches in different positions and taken from parts which were subject to different temperatures during the welding process. And the idea was to compare their total impact energy along with its components to see if there is a significant difference. So once again, we can conclude that the temperature resulted in slightly higher ductility, and the location, well, the root notches on the root side had higher crack initiation energy, but lower crack propagation energy, whereas this ratio was more favorable for the weld face. So if we manage to create a welded joint without any cracks of relevant size, we would definitely favor a crack in the weld face side, because it would take the root side, because it would take more energy for it to initiate. But if we already have cracks, which is a more realistic possibility, then the other case will be more favorable, because it takes a lot more energy for that crack to propagate to its critical length. So thank you for your attention.